Good day all. I hope you're safe and sound from the Chinese Wuhan virus and the Chinese expansionist policies and the Chinese harboring the terrorism. At this point of this point, what I like to emphasize in each and every lecture is because today what we got, the Wuhan virus, the coronavirus or Omicron virus has originated from China. The only way how we can basically show our resentment is to boycott the Chinese products. Coming to my 31st lecture, ladies and gentlemen, all mariners, whatever support you have provided me, I thank you for all that. I do still answer all your queries as in how I've been asked for. And I take this opportunity to help you out from all the aspects, from my little expertise of my 4 decades of sea career as a mariner and almost 2 decades as a master and mooring master. Today's agenda, the subject matter would be, it's something which you have not come across so far. As you know that I'm always delivering all these lectures on an extempore without editing or anything. Therefore, today's agenda is about when a vessel goes into the locks, because when the vessel passes from locks, she traverses through from one density of water to another. So in this particular lecture, the lecture number 31, I'm taking this perception that the vessel is passing from the sea water to the fresh water, that is inbound. Now, the thing which I would like to highlight is, or I'm trying to highlight is that how does the hydrodynamical forces work with that? Prior to that, we need to understand something about the Bernoulli's principle. How does the sea water and the fresh water interacts between both the different density waters that we'll see. So I'll right now focus onto my laptop where I have drawn few things or I've assimilated the data for the hydrodynamics interaction between 2 densities of waters. How do they work? So please pay attention right now on the laptop what I'm going to project to you all. Thank you. This is the scenario when this is the fresh water and this is the sea water. The sea water being more dense juts under the fresh water. So you can see the breaker over here. The breaker over here basically signifies and implicates how does the interaction takes place between the sea water and the fresh water. The sea water is on the right side of the computer and the fresh water is on the left side of the computer. As I go on to the next slide, you can see very clearly, this is an example taken from a river mouth where the sea water and the fresh water interacts. You can see this is an example taken from state of Georgia, the salty part where the sea water is going under the fresh water and the fresh water is going above the sea water. You see all those things, the riverbed, everything has been, depicted over here. That is the interface between the sea water and the fresh water at the river mouth. Going to the next slide. You see in this similar scenario, if I start from the previous slide, how the sea water and the fresh water are interacting, this is how we see here. The fresh water, which is less dense, density 1.0, is surfacing the salt water. Now when the salt water is coming over here, it is basically jutting down and creating a wedge over here. As you can see the wedge over here. So this wedge is something what we need to be careful about because it not only juts down under the fresh water but also creates turbulence. Therefore, coming to the next slide, as you can see, the wedge effect with turbulence. You can see in the similar, taking the call from the previous slide, how the fresh water and seawater are interacting. The seawater is jutting under the fresh water, and the next slide, as you can see, it is jutting under the fresh water, and the turbulence, you see the turbulence, how it is created. Because this is fresh water, then it becomes little more salination or brackish water and the seawater. But the seawater rises because of the tide current effect, and you see what sort of turbulence it can encounter. Therefore, it is depicted in this particular slide, the wedge effect with the turbulence. The wedge effect with the turbulence, how it creates and what sort of things may impact when the vessel is entering from a seawater to the freshwater lock gate. We'll talk about it when I come on to my little board, which I will try to explain it with all the explanation and with all the logical conclusions. Prior to that, we must understand the Bernoulli's principle. The Bernoulli's principle states the total mechanical energy of the moving fluid, comprising the gravitational potential energy of the elevation, the energy associated with the fluid pressure, and the kinetic energy of the fluid motion remains constant. The same thing I've depicted on my board, on my whiteboard, the Bernoulli's principle, where it says an increase in the speed of the fluid simultaneously with a decrease in the pressure or a decrease in the fluid potential energy. Now, let me move this laptop from here and explain you the thing in details. On the left side of this board, I have drawn a kind of a recap where I've shown here with respect to the right side of the board, as you can see. Now, the same thing has been, which is on the left side of the board, has been enlarged, which I'll talk about it a little later. What is happening? There are few properties which we must take into account. The seawater, when the vessel is entering from seawater to the freshwater, be it Panama locks or any other locks, you must understand that the seawater is at low level and the freshwater, be it a Panama Canal, Gatun Lake or anything, is at low level. So when the vessel, you see here, when emptying out the locks, the chamber water is released downstream. Now in this case, bear in mind that this is upstream going up northway, and southway or southwards is a downstream. So the vessel is going to enter from here, that is from seawater, which is downstream, to upstream freshwater river or lake. Now see what happens when vessel emptying the locks chamber when the water is released, that it is released to the downstream. There will be a positive surge in the reach of the lock gate. When the vessel is coming, which I will depict it in the next slide, when the vessel is approaching from the seaward side towards the freshwater side, there will be a positive surge. Why positive surge? Because the freshwater is pushing, the seawater is pushing with gradient, because you see this area, this is the bank area where the area is large. This is coming with the Bernoulli's theorem. If I look at this, there is a large area of water which is pushing, and there is a constriction. Constriction, I'm taking this as a lock, and then it is coming upstream. As it is saying, as what we talk about, this is the high pressure area depicting on the board, and this is the low pressure area. Low pressure, that is the velocity is more, and it creates turbulence due to change of the density. Now that goes with the Bernoulli's theorem. And the high pressure area is this, the one depicted with the blue, and another high pressure area on the freshwater side is depicted again with the blue. But in between there's a lock where the vessel is going to traverse or pass. What is happening? It is a low pressure area, because the same volume of water has to pass. The pressure here is high. So what it is doing, it is pushing the vessel when she's entering the lock over here. And the pressure here is high and it becomes low and then again high. So she's traversing from high pressure area to low pressure area, then to the high pressure area. Now that is where we do experience the bow and the cushioning effect, which we'll see in due course. Now try to understand, when a vessel is coming from the seaward side, it is broad. But the locks are made normally in rectangular form or square form. What is happening? The seawater with so much of high density and with broader area, as it is depicted over here, is pushing the water into the lock, which is same thing. That is the reason I talked about initially the Bernoulli's theorem. In high pressure area, the pressure is high and velocity is low. In low pressure area, the velocity is high and pressure is low. Now try to correlate the same thing coming from the sea to the lock being the low pressure area, but the velocity is high because the same amount of water or the underwater volume of the displacement has to pass through that because it's a continuous synchronous process. Therefore, the high pressure area is passing from here into the lock. The velocity here is less, but the pressure is high. The velocity here is more, but the pressure is low. The velocity here is less, but the pressure is high. Once we understand this point of view, because this is upstream as depicted here and the fresh water. This is the downstream and the seawater. Then this becomes the positive. There is a positive surge here and there is a negative surge over here. Why? Because when we talk about the positive surge, the vessel with 1.025 density or seawater density will rise. In fresh water, the vessel will sink more to cope up with the loss of underwater volume of displacement. And that is the reason. Please mark and remember this. The positive surge in the reach, which is there from the seawater side, and upstream there's a negative surge in the reach when the vessel is traversing. Vice versa, when the vessel is coming from fresh water to seawater, it will happen in the similar manner. But at this point of time, I am trying to explain you when the vessel is traversing from the seawater towards the fresh water through a lock gate. Do not forget these 2-3 things what I am talking about, because it will help you to understand that in this area, before entering the lock, there's a high pressure area. Inside the lock, because of, as per the Bernoulli's theorem, there will be a low pressure area. The velocity will be more. Here the pressure will be more. Here the pressure will be less, but the velocity will be high. Now, if we have understood these 2-3 things, that is the reason I am trying to emphasize and stress upon them. Now we come to understand how does the Bernoulli's theorem, Bernoulli's principle, as per the Bernoulli's principle, how do the two different seawater and the freshwater densities, how do they interact? As what we spoke earlier in my computer slide, that the fresh water being lighter jutters over the seawater, and seawater being heavier than the fresh water goes below the fresh water and jutters down, creates a wedge. Because of the wedge, there's a turbulence, underwater turbulence created. Now we are going to see step by step how the underwater turbulence is created. So, Bernoulli's principle we've talked about. Here the vessel is entered. This vessel which is entering into the lock. What is happening? She is getting pushed by the high pressure area. So what is happening in figure number 1? Let me put it like this to make us understand. Number 1, number 2, number 3, 4, 5 and 6. Now see what is happening. When the vessel in as depicted in figure number 1 is getting pushed as per the Bernoulli's theorem, is pushed into the lock at a higher speed. At that point of time, the speed has to be reduced whenever we have the pilot on board, and the master also has to exercise the due diligence, because the water is entering with a high pressure into the low pressure area. But here the velocity is very high. Because the velocity is very high, the underwater currents will be very strong, because it is getting constricted into the lock. Therefore, when the vessel is entering from here, from the high pressure area into the lock to the low pressure area, which is depicted for the lock, what is happening? The pressure is high, but here, as per the Bernoulli's theorem, which is marked over here, what is happening? Here the pressure is low, but the velocity is high. So the speed has to be reduced, and of course, tugs have to be made fast prior to approach, which I have not shown here, in order not to make it very claustrophobic. Therefore, figure number 2. Now what is happening? Because the vessel here is getting pushed. Now she is getting pushed more towards the wall of the lock because of the high pressure. But the velocity is also there. So this is a critical point where we have to take care of the vessel's movement, and of course tug also has to be made fast, which, as I said, I've not shown here. If you have any queries, I can answer it thereafter. Figure number 3, when she's already coming alongside. Now here, because of the high pressure which is marked over here, it's facilitating vessel to push her inside the lock, and the velocity which is developed because of the underwater current. Now mark my words, when I said the fresh water and the sea water, how do they interact? The fresh water rides over the sea water, and sea water creates underwater turbulence. I can understand here in this part of area there might be brackish water, but there's a difference in the density. The more the difference in the density, the more the gradients between two different densities of water, there'll be more turbulence underwater. And what I'm telling you, what I'm teaching you here, gentlemen, ladies and gentlemen, you will not find it in any of the books. I can assure you this, because I've done loads of research on this. Now, from this point of view, when we come to this point, that is figure number 2, she is getting pushed into the, let's say, starboard side of the vessel, and this side, right side of the lock gate. Figure number 3, she's made fast till such time the locks are getting closed and the water is, pumped in or pumped out, as what we said. The water is always pumped out on the lower side from the higher side. This is the higher side because river being on the higher side, in case water has to be pumped in, it has to be pumped in from the higher side and pumped out into the low side. And low side, when we talk about sea water, it is creating a positive surge in the reach, and that's what I mean. The positive surge in the reach, it is getting pushed into the lock. Now, take care. Now, how do we experience the hydrodynamical effect in this particular lock? That is what I talked about, the banking and cushioning effect, the piston effect provided due to transition of the waves trapped in the gap between the ship and the lock gate. Now mark these things. Please do take a note of this particular thing which is mentioned on the right side. Now let's take this perception that figure number 1, she is being pushed in, the pressure is low, and once she comes into this, the pressure is high, the pressure is high here, and she is getting pushed in. Once she is inside the lock, and let's say the lock gates are closing when she is made fast, the pressure is low but the velocity is high until such time this lock gate which is already closed. Now because this lock gate is closed, is already closed before she is entering here, this lock gate gets closed when she has already entered the ship, entered the lock. There is certain amount of piston effect which is taking place here. That is what we are talking about, the piston effect. That is when the vessel is at phase number 3 or figure number 3, what is happening? The lock gate is closed here and the vessel is inside here. I will just take out this diagram for you to understand it properly. I will just take this out and explain you better. Now here in this case, number 3, the lock gate is closed. The lock gate is closed and the vessel is at number 3 is made fast. So what is happening? Because here the velocity was high, it is creating another turbulence because this part of the lock gate is closed, which is on the freshwater side, that is the upstream, coming from this figure, coming from this diagram. So there is, as it is, underwater turbulence created even when she is made fast and when the water is being pumped out, pumped in, when the water, because she is going from seawater to freshwater, so there will be a negative surge in the vessel in the reach. That is, when she is entered from seawater to the lock and going to the freshwater, there will be a negative surge in the reach. When the negative surge happens, what happens? Try to understand, because inside the lock there is a brackish water coming from sea and freshwater. The brackish water, she will have a certain amount of sinkage. Once the sinkage is there, what will happen? There is a possibility for her, in case her UKC is very less, she may probably run aground because of this effect. And in case if the drafts are okay and all those surges effect, that is the negative surge effect, because she's coming from 1.025 to brackish water of, let's say, 1.012, and here it is 1.000 density water. So there will be a negative surge by virtue of which she may sink more to cope up with the underwater volume of displacement. This effect enhances furthermore. How? In case there is another vessel tied up. Let's say this vessel is tied up in figure 4 over here on the starboard side of the bank, and this vessel is already tied up, and this vessel is also tied up over here. So what happens? Once the lock gate closes, the underwater volume of the displacement of the vessels, bigger vessel or the smaller vessel, which I explained you in my first and second and third lecture, that is the mantra. What happens? There will be a gradient formed between 2 or 3 vessels which are depicted over here. For that, she may surge. This is while she is inside the lock. So be very careful. I would ask or urge all the masters to ensure whenever your vessel is entering inside the lock, make sure that you do not get constricted with the congestion of too many vessels in the lock. You as a master, please do exercise your overriding authority in consultation with the pilot. In case you find your vessel is big and there are too many vessels which will be entering into the lock, please hold on, do not enter, because the effect what we'll see, you'll realize what I'm trying to talk about. That is when the lock gate opens on the freshwater side. You will see that. So I just take out this line from here and explain you that, okay, when the lock gate opens over here, what happens? The vessel was inside the lock earlier and the lock gate opens. The seawater, the fresh water and the brackish water. Let's take this as brackish water because the seawater, fresh water mixed, because water is interfacing at all the times whenever the vessels are traversing either from south to north or north to south. But the problem experienced here, because of the same thing, there is a difference in the gradient of the density. This is the brackish water here. This is the seawater, this is the brackish water. Now because of that, the fresh water is going to go over the brackish water, and with the brackish water and with the effect of the piston effect, which was experienced when the lock gate was closed, see what will happen. When the vessel is casting off, I'm taking this particular vessel, when the vessel is casting off, what will happen? There will be water ingress over here, and what will happen? It will, in this particular scenario, it will cant your bow more to port, and your stern will go very close to starboard, even if you have two tugs made fast fore and aft. I have experienced this. Even if you have two tugs made fast fore and aft, that is, if I take out this all figure and let's say there is a tug over here, one tug over here and one tug at the bow, you will still not be able to control this in case you don't have enough sea room in this area. If you have enough sea room, the tug can pull you out, and that is the reason I was trying to explain and emphasize that please, from the master's perspective, whenever you're entering the locks, please do ask your pilots that if there is a congestion and you're a bigger vessel, hold on, abort. Exercise master's overriding authority. Think about it that if your vessel is here and there is another vessel over here, I'm drawing this over here, there is another vessel over here, and if the tug is trying to pull you out, where is he going to go? Because there is not sufficient sea room here. In return, what will happen? Because of this bow and cushioning effect, the bow and cushioning effect, what I've talked about over here, the vessel is going to cant more to port and your stern will be touching to the starboard. Even after you give the helm, because even though if you give the dead slow ahead or slow ahead, it will take few seconds to build up the revs. But the time is too short. Your vessel will be coming very close to the lock gate, to the side of the lock, or may bang the lock. In case if you have another vessel very close to you, in this case I've shown the separation, but also mark my words when I say underwater volume of displacement, which I've explained you in my first, second and third lecture respectively. If this is the vessel which is going out first, the underwater volume of displacement, what she is catering, will create a negative effect, a vacuum here, and the water will gush down faster and the water finds its own place. So here, now it is opposite to that. What we saw here, the pressure is more. So the pressure is more, and in this case the pressure is less, but the velocity is high, coming to the Bernoulli's theorem. Because of that, we experience a banking and cushioning effect. Let me explain you this again, just to make sure that I'm not jumping. When we passed from here, the pressure was high. Here the pressure was low because of constriction. Now, you reciprocate the same thing when we are coming to the freshwater area. Freshwater, when the lock gate is open, here again it's a high pressure area, what I've depicted over here. High pressure area jutters down here. But here, because there is a constriction, as per the Bernoulli's theorem, what happens? The pressure is less, but the velocity is more. Now, this particular velocity is making you cause for the vessel to go more to port or cant more to port in this particular scenario, and you may have an interaction or touching of your stern or the quarter to the bank, this side, and that is what we experience, the bow and cushioning effect. And when this effect is going to be there till such time we are well passed and clear into this area, approximately here, till such time we are passed well clear of this area, we will keep on experiencing this bow and cushioning effect. Until such time the pressure gradient neutralizes. In other words, here as we can see, when the vessel is entered into the freshwater area upstream, starting from here, the pressure gradient is neutralized, then the vessel will be steadied out. By such time, the vessel has picked up the speed. But here, you will experience, even though if you are given half ahead, or hypothetically full ahead, the engine will take lots of time to gear up with the revs. Why? Because the velocity of the pressure of the water which is ingressing into the lock from the freshwater side is very, very high, because the pressure is low and velocity is high. So be careful about this particular aspect, and this effect will be there predominant with you till such time you're well clear of the locks, maybe up to here, at least approximately, as per the practical experience of mine, approximately about 1 mile away from the lock, you will keep on experiencing this gushing or the Venturi effect. This can also be construed as a Venturi effect because there's a vacuum created, and because of this vacuum, you will have a very tough time, especially in particular in case you have another adjacent vessel close to you, or if you have a bigger size vessel inside the lock. Because of the underwater volume of displacement, it will create a vacuum, which in return will create a Venturi effect. And this effect will be there till such time you're well past clear of the lock, approximately 1 mile from the locks, approximately. Now, ladies and gentlemen, this particular lecture, it took me a lot of research with the explanation. I'm also imparting lots of lectures for few companies on hydrodynamics, on ship handling, and STS ops. All these are based on my practical and pragmatic experience. I would urge you all guys, please come back to my queries because to me with all your queries, whatever you wish to ask me, because that helps me to basically, impart whatever you would like to ask me, and also gives me food for thought and encourages myself. Once again, thank you very much for your time and your patience. Please do like, subscribe, share, press the bell icon on this lecture. Thank you. God bless. Good day.